In 1955, a crane lowered a Caterpillar D8 from a ship toward the ice of McMurdo Sound. The machine had been built to push Earth. Here, it was being lowered onto Antarctica. A U.S. Navy artwork from Operation Deep Freeze records the moment. That is the contradiction. This film follows the D8 into jobs where ordinary access and traction were not enough. But the tractor was never the whole story. Operators. Mechanics. Attachments. Parts. Crews. The machine worked because a system worked around it. So what happened to the Caterpillar D8? How did that model name survive from the 1930s into an age of electronic controls and electric drive? To answer that, we have to go back to the problem that came first, the ground. At the start of the 20th century, farms, logging camps, and road crews already had powerful traction engines. But power was useless if a machine buried its wheels in soft soil before it could pull a load. This is the physical problem that continuous tracks attacked. A wheel concentrates weight on a relatively small contact patch. A track spreads that weight across a longer footprint while giving the drive system more surface through which to apply force. The machine is still heavy. The ground simply experiences that weight differently, and the tractor can search for grip across many track lengths rather than at one narrow tire contact. On November 24, 1904, Benjamin Holt's company staged a practical demonstration of a track-type tractor on the peat of Roberts Island near Stockton, California. ASME identifies that experiment as the beginning of a design line that would influence agriculture, logging, construction, road building, and transportation around the world. The tractor was patented and in production by 1907. This was not yet the D8. It was not even the Caterpillar company that people recognize today. But it established the first principle of the later machine: do not demand that difficult ground behave like a finished road. Bring a machine that can create its own moving foundation. Tracks were not magic. They wore pins, bushings, rollers, idlers, and links lived in dirt, water, abrasive rock, and shock load. A crawler exchanged one set of limitations for another. It gained traction and flotation, then demanded inspection, adjustment, lubrication, replacement parts, and skilled judgment. That trade would define the D8 for the next century. And it created a second problem. Once a tractor could reach difficult ground, what exactly would it do there? In 1925, the Holt Manufacturing Company and the C.L. Best Tractor Company merged to create Caterpillar Tractor Company. Caterpillar's own history describes the combination as more than a factory merger. Holt brought the Caterpillar name, manufacturing capacity, and global reputation. Best brought advanced tractor design and a strong dealer foundation. That is a company account, but it points to the structure that matters. A heavy machine has little value if it cannot be delivered, maintained, and supplied after the first sale. The next change was fuel. Gasoline tractors could provide useful power, but long industrial duty rewarded fuel economy, torque, and durability. Caterpillar began producing the Diesel 60 in 1931. The company later said that 10 of the first 25 Diesel 60 tractors worked on Belgium's King Albert Canal, operating through a long construction campaign. Then came the name. In 1935, Caterpillar upgraded its diesel line and introduced the RD4, RD6, RD7, and RD8 designations. 2 years later, the R disappeared. The RD8 became the D8. Even Caterpillar's corporate history treats the meaning of RD as unresolved, so any confident explanation today is more legend than evidence. The important continuity is not the missing letter. It is the decision to organize machines into a recognizable diesel family. A model name creates expectations. It allows buyers to compare generations, dealers to stock around a population of machines, mechanics to accumulate knowledge, and attachment makers to design around known dimensions and duties. The D8 name could survive only because Caterpillar repeatedly changed the machine beneath it. That is the first paradox of the D8, continuity required redesign. Early D8s were cable-controlled, open-station machines with mechanical systems that asked a great deal from the operator. Later machines added hydraulic control, stronger structures, different engines, improved steering, protective cabs, elevated sprockets, electronic management, and digital assistance. If we line them up, they do not look like one unchanged tractor. They look like a family that kept the same job while absorbing new technology. But the job itself is often misunderstood. A tractor does not become a bulldozer merely because it has tracks. A familiar image of a D8 is a crawler pushing dirt. But the tractor was only the power unit. A 1941 Library of Congress photograph at the Kingsbury Ordnance Plant shows a Caterpillar diesel D8 pulling a Laterno carryall scraper. The caption records a 9-hour working day, an average 10-yard load, and a 300-yard haul. Those figures describe that photographed job, not every D8. The important detail is the combination. The crawler supplied traction. In this documented case, the scraper turned that traction into a cut-carry spread cycle. The working unit was no longer the tractor alone. Then the operator had to make the combination work. Push too deep and the tracks slip. Load too aggressively and the machine loses its useful rhythm. Read a slope badly and traction becomes danger. The operator listens to the engine, watches the track, feels the load, and preserves the grade that the next machine will inherit. This is why horsepower alone cannot explain the D8. The useful machine was the tractor, the attachment, and the person who knew how to make them work together. And during World War II, that flow became a military resource. Armies and navies do not operate only through weapons. They operate through surfaces. Aircraft need runways. Fuel needs roads and storage. Ships need bases. Trucks need grades they can climb and ground that will carry their weight. A captured island is not yet an airfield, and a remote coast is not yet a supply route. The U.S. Navy created the Seabees in 1942 to build in combat zones. Naval history records that Seabee units developed more than 400 advanced bases across the Atlantic and Pacific theaters. On Guadalcanal, construction crews repaired Henderson Field under repeated attack. In the Marianas, they repaired and expanded airfields that connected the campaign to long-range air power. Henderson Field reveals what a bulldozer meant inside that system. Bombing could turn a runway into a sequence of craters, but the airfield had to remain available to aircraft already committed to the battle. Naval history describes Seabee crews filling damage and relaying the surface again and again, keeping the strip in use while attacks continued. The engineering job was therefore not build an airfield and leave. It was preserve an operating surface faster than the enemy could destroy it. On Saipan, Seabees began repairing the captured Islito airfield and returned the strip to operation within 4 days. On Tinian, their bulldozers reshaped damaged and unfinished airfield ground while the campaign was still active. The sources do not identify every crawler by model, and this film will not pretend they do. What they establish is the strategic role of earthmoving. Construction time could be converted directly into flight operations. Bulldozers were part of that transformation, but they were never the entire transformation. Surveyors established grades. Demolition crews cleared obstacles. Quarry crews produced aggregate. Truck drivers fed material to the work face. Mechanics kept engines, cables, tracks, and final drives alive. Operators worked in heat, rain, coral dust, mud, and enemy fire. A dozer could push a crater closed, but only an organization could keep the runway operating. That distinction protects the story from mythology. Caterpillar's corporate history says the company produced approximately 51,000 track-type tractors for military use during the war. That is a manufacturer figure for all military track-type tractors, not a D8 production total. It tells us the scale of mechanization without allowing us to pretend that every crawler in an archive photograph was the same model. The record places D8s within a broader wartime construction fleet. Their value depended on whether construction units could transport them, fit them for the job, and keep them operating. No source supports treating every wartime crawler as a D8. Its military value was the time construction machinery could remove from the interval between arrival and operation. Every day removed from building an airstrip or access road could move aircraft, fuel, food, medical supplies, and ammunition sooner. Earth-moving machinery compressed the interval between arrival and operation. But the machines did not compress that interval equally for everyone. The Alaska Highway exposes the human cost hidden inside the heroic construction image. After Pearl Harbor, American planners feared that Alaska was isolated and vulnerable. In cooperation with Canada, the United States approved a road from Dawson Creek toward Fairbanks. Army engineers began construction in March 1942. The Corps of Engineers describes a 1,685-mile route, built first as a crude military road and later improved toward permanent highway standards. The landscape resisted the schedule. Muskeg could swallow vehicles. Permafrost could remain stable until construction exposed or warmed it, then collapse as the ice-rich ground changed. Floods damaged early work. Landslides buried equipment. Crews used corduroy road, layers of logs and vegetation, to cross terrain where ordinary fill would disappear or thaw the ground beneath it. Bulldozers appear throughout the record. But the popular temptation to count them, identify them all as D8s, and let the machines become the protagonists creates a false history. The National Park Service documents a sharper contradiction. The Army deployed segregated black engineer regiments to Alaska and Canada while maintaining discriminatory assumptions about who could operate heavy machinery. Many black soldiers from the Deep South were initially denied the equipment given to white units and worked with picks, shovels, and axes under brutal conditions. They still completed major sections of the route. The Corps records 10,607 Army engineer soldiers on the road, including 3,695 African American soldiers. Those totals matter because they restore human scale to a story often reduced to machines and mileage. At Beaver Creek on October 25, 1942, Corporal Refine Sims Jr. of the 97th Engineers and Private Alfred Jalufka of the 18th Engineers met as the road sections joined. The photograph includes bulldozers, but its historical subject is not steel. It is labor, military urgency, segregation, and achievement. The schedule did not erase the inequality. Black units completed difficult work while being denied equal access to towns, relief, and in many cases the same machinery. The machines increased capacity, but the institution still decided who received that capacity. The Pioneer Road opened to military traffic in November 1942. It later supported airfield construction and the transfer route for Lend-Lease aircraft, and it opened to civilian use after the war. Even opened needs qualification. The first achievement was a rough military road, not the finished highway remembered today. Army engineer units continued to improve and maintain it through the winter. Civilian contractors working under the Public Roads Administration then took over much of the upgrading and permanent work. The road was not a single burst of bulldozer power, it was a handoff from reconnaissance to pioneer construction, from temporary crossings to improved grades and bridges, and from wartime need to a peacetime route. That sequence explains why speed and quality were in tension. A pioneer road could move urgent traffic before it met civilian standards. Later crews could straighten, drain, bridge, and stabilize what the first crews had forced through. The equipment helped create access for the next phase, but each phase required a different balance of urgency, durability, labor, and material. The lesson is not that a D8 built the Alaska Highway. The lesson is that mechanical capacity matters only through decisions about who receives it, who is trained to use it, who absorbs the danger, and what purpose the new route serves. That question followed the D8 into the post-war landscape. After the war, crawler tractors moved from military urgency into long construction programs. Their importance was not that they replaced every other machine. It was that one power unit could keep moving between stages of the work, opening a route, pushing a scraper, spreading fill, recovering equipment, and preparing the ground for the machines that followed. That is what Reshaped America means here. The tractor did not choose the road, approve the project, or decide which landscape would change. People did. Machinery changed how much of those decisions could be turned into physical work. Then Operation Deep Freeze took the same question beyond ordinary soil. Caterpillar's history says its 1955 Antarctic equipment used a special low-ground pressure undercarriage. The Navy's own collection identifies a D8 being unloaded during Deep Freeze. Together, those sources support a narrow claim: the D8 platform was adapted for polar logistics. They do not prove that the tractor conquered Antarctica or operated without failure. Low ground pressure is not about making the machine light. It is about spreading its weight across more track in contact with the surface. On snow and weak ground, that can be the difference between moving and digging the machine into its own path. But Antarctica exposes the limit of the heroic machine story. A tractor on the ice still needs fuel, starting procedures, transport, shelter, spare parts, trained operators, and a crew willing to work in extreme cold. The machine extends the reach of the expedition only while that support chain remains intact. The same principle applied back home. A crawler could make a plan physical. It could also accelerate a bad decision. Mechanical capacity contains no moral judgment, it multiplies the intentions of the people who deploy it. And because that capacity was expensive, owners needed more than a powerful first day. They needed the tractor to remain productive after the photographer left. A D8 working far from a factory is a promise under stress. The tractor earns its place on a project only while it can keep working. Caterpillar's history says that after the 1925 merger, former Holt and Best dealers formed a global network, and that parts delivery by air was available by 1928. Those are manufacturer claims, but they change what the product actually was. The tractor arrived with an industrial network behind it. At minimum, the network changed the availability and movement of parts. The contractor still needed mechanics and inventory. The network did not prevent failure, it gave owners a repeatable channel for support. That distinction becomes more important as a fleet grows. One machine can survive on improvisation. Dozens of machines require common procedures, known components, scheduled work, and people who understand the same design family. Standardization turns repair knowledge into capacity that can move between jobs. Caterpillar's modern remanufacturing program extends the same economic logic. The company describes major components moving through return, inspection, disassembly, restoration, assembly, and testing rather than treating the entire tractor as disposable. That is manufacturer material, not an independent measure of cost or life. So, what happened to the D8 has an unusual answer. It did not simply survive. Its support system survived with it. But continuity brought a harder obligation. The machine had to become safer for the person inside it. Look at an early D8 and the vulnerability is obvious. The operator sits above moving tracks, exposed to weather, dust, noise, vibration, falling material, branches, and rollover risk. Controls demand force and coordination. Visibility is limited by the machine's own structure and by the material rising in front of the blade. Experience helps, but experience cannot repeal gravity. As construction equipment grew more capable, safety rules and litigation made the operator's exposure part of the public record. The story shifted from whether a machine could perform the work to what protection should be expected while it did. OSHA's construction rules explicitly include crawler tractors in the equipment covered by its rollover protective structure requirements. The standard addresses minimum performance, mounting, labeling, and qualifying earlier governmental requirements. It does not tell us that every historic D8 was unsafe in the same way. It tells us that rollover protection became a formal system requirement rather than an optional gesture. The wording is revealing. The scope covers crawler tractors with or without attachments. A protective structure removed for any reason must be remounted with equivalent or better fastening. The structure must be labeled for the machine it is designed to fit. The rule also recognizes earlier requirements from California, the Army Corps of Engineers, and the Bureau of Reclamation. Safety had become something that could be specified, inspected, documented, and traced to a particular machine configuration. That is a different kind of standardization from a common engine or track part. The regulation turns protection into documented requirements for a defined machine configuration. Court records also show how responsibility was contested. A Wyoming Supreme Court case involving a Caterpillar D8 examined claims after a fatal rollover and debated the relationship among machine design, protective equipment, warnings, and user decisions. One lawsuit cannot define the safety history of an entire product line. It does show those questions being argued through law as well as engineering. Modern cabs reduce exposure and fatigue, but they introduce new layers, sensors, displays, cameras, electronic controls, climate systems, and software. The operator is better protected and better informed, while the service organization must support a more complex machine. Progress therefore changes the failure modes. It does not abolish them. The next major redesign made that truth visible from hundreds of feet away. For decades, crawler tractors carried a low-drive sprocket within an oval track profile. Dirt, shock, and undercarriage motion lived close to the powertrain. In 1977, Caterpillar introduced an elevated sprocket design on the larger D10. The drive sprocket moved upward, separating more of the final drive system from the track roller frame and giving the machine its unmistakable triangular profile. Caterpillar then extended the high drive concept across other tractor sizes. The D8L joined that family in 1987. The visual change was dramatic, but the design question was familiar: how do you keep delivering tractive effort while making a punishing system easier to protect, balance, service, and control? High drive did not make undercarriage wear disappear. It rearranged the system so shock, ground contact, machine balance, and powertrain placement could be managed differently. Caterpillar's own account emphasizes durability, serviceability, balance, and ride. Those are manufacturer claims, but they explain why the concept persisted. The D8 model family later absorbed the change, that is continuity of a product name and job class, not proof of unchanged mechanical lineage. That matters because industrial buyers can be conservative for rational reasons. A new architecture must prove not only that it works, but that parts, training, resale, transport, and repair can follow it. The familiar model family gave Caterpillar a way to introduce a radical silhouette without asking customers to abandon the service ecosystem around the name. Eventually, electronics began performing tasks once left entirely to operator feel. Sensors could estimate load and slip. Guidance systems could compare the blade to a digital design. Cameras could expand visibility. Automated transmission logic could keep power within a useful range. The machine was becoming an information system. And in 2026, Caterpillar announced a D8 that changed the path from engine to tracks again. The D8XE still begins with a diesel engine, a Cat C15. But instead of sending power through a conventional torque converter arrangement, the engine drives a generator. Electricity powers a motor connected to the final drives. That makes the new D8 a diesel-electric earthmover. Caterpillar says its internal comparison found lower fuel use and higher material movement than a standard D8 in a composite test cycle. Those are manufacturer test results, conducted under stated conditions, not a universal guarantee. Caterpillar also says the electric drive path has fewer moving parts than a conventional transmission. The source-supported historical point is architectural. The route from diesel engine to final drives has changed again. The cab now belongs to a common design shared across several Cat dozer sizes. A touchscreen presents machine information and assistance. Optional systems monitor blade load, track slip, slope, steering, and visibility. Remote troubleshooting and software updates connect the machine back to the dealer network. This changes the relationship between skill and standardization. Physical feedback has not disappeared, but the modern machine can add measured feedback and assistance. Caterpillar presents the common cab as a way for operators to move more easily between machine sizes. That is a manufacturer claim, yet it repeats a very old D8 strategy: make knowledge portable across a family. Remote troubleshooting extends the service network into the software age. Caterpillar says its remote troubleshoot feature allows a dealer to diagnose problems without a call-out, while remote flash supports over-the-air updates without a software engineer in attendance. That does not remove mechanics, operators, or field judgment. It adds another layer of dependence. The working tractor is now connected to diagnostic systems, software support, and communications infrastructure as well as fuel and parts. The circle is almost complete. In 1904, the breakthrough was a moving foundation, tracks that allowed a heavy machine to work where wheels sank. In 1931, diesel made long industrial duty more practical. In the 1930s, the D8 name organized a machine family. Attachments converted traction into different kinds of work. Wartime construction proved the value of mobile earthmoving under extreme pressure. Dealers and rebuild systems made the machine repeatable. Safety rules forced the operator's survival into the design brief. High drive rearranged the relationship between powertrain and ground. Electric drive and software now rearrange it again. What survived was not one engine, one blade, or one shape of track. What survived was the system. The Caterpillar D8 did not build America by itself. People selected the routes, drew the plans, approved the projects, operated the controls, repaired the failures, and lived with the consequences. Other machines dug, hauled, graded, lifted, drilled, and compacted. The D8 was one participant in a much larger industrial network. But it occupied a decisive position in that network. It stood where intention met terrain. Its tracks made difficult ground negotiable. Its attachments turned traction into clearing, cutting, pulling, ripping, and spreading. Its dealer and parts system made that capacity repeatable. Its continuing redesign allowed one model name to cross from open cable control tractors to protected, sensor-rich, electric-drive machines. That is what happened to the D8. It did not remain the tractor that reshaped America. It became the operating system through which generations of operators kept reshaping it. If you want the next story to examine another machine hidden inside America's infrastructure, tell us which one should come next.